Good morning, sir. Everybody, please respond. Program has already started or not? Nothing to hear from.
Good morning, Doctor Sir. We will be starting at 10:30 actually.
Yeah, okay, okay, sir.
Uh,
Because nothing is right.
no, no,
Thank you.
we will be starting at 10:30, sharp 10:30.
Okay, okay, sir. Thank you. Have a nice day.
Hello.
Good morning, sir. Good morning. Good morning,
Good
Dr.
morning,
Tokunagi. How are you?
Dr. Mera.
Yeah. So greetings from India.
Greeting from Japan. We have much snow.
Yeah.
Very cold.
We are also having winters in our area.
So can you see my slide?
Yeah, I can see your slides, but we will be starting within 10 minutes.
Yeah. Can you see my slide?
Yeah, I can
shared
see your
my screen.
slides.
You can't see.
I can see, but they are not moving actually. You can make it full screen also.
Okay, wait a moment. Oh, what can I do? I don't know how to.
There might be some at the bottom border. There might be some. You can press F5 also.
F5?
Yeah.
No. Okay. Not F5. This is. No. Wait a moment.
The bottom of the right, just before the minus sign, there is a logo. Just click it.
Can you see my first slide?
You have stopped
see?
sharing, sir. You have stopped sharing. Yeah.
The next.
Yeah. In this way we can see, but
Next.
yeah.
Can you see new slide like this way?
Yes, yes.
It's okay.
Of course, it's okay, but if you can do it full screen also, like there is a at the
Full
bottom
screen.
there is a glass type of a structure.
Full screen.
At your screen, phone screen, at the bottom of the border.
This one. This one?
There is a glass.
What? Let me see. Networking. That's okay. Wait a moment. Can you see my slide?
You have stopped sharing, sir. You just share.
I'm changing a slide. Wait a moment. The title.
No, it's not shared, sir. Please share your slides.
Okay.
Yeah.
Can you see?
No, we can see your screen of your desktop or laptop, whatever you are using, but not the slides.
Oh. How about this?
Still not.
Wait a moment. Okay. How about this? All right.
Yeah. No, it's okay, sir. No, it's okay.
Okay. But
You can move your slides also. So that
not that. I don't know why. What's happened?
Yeah, they're working.
Moving?
Yeah, they're
Talking?
moving. Yeah.
Moving?
Yeah, they're moving.
Okay. It's okay?
Yeah.
Okay. Is it okay?
Yeah. It's okay. Neha, are you there?
Yes, sir.
So you could start within 5 minutes, or you could start right now because Dr. Tokonami has already joined, so he can join his start his lecture at 10:30.
Okay, sir. Good morning, respected foreign faculty expert, Professor Shinji Tokunomi, sir, our course coordinator, Professor Rohit Mehra, sir, and faculty members of the Institute. Dear participants and my colleagues, a warm greeting for the day to all of you. I am Neha Bharti, PhD student of Professor Rohit Mehra, sir. It gives me immense pleasure to welcome you all to the GIAN course on environmental radioactivity monitoring and its impact for health risk assessment, being organized in virtual mode by Professor Rohit Mehra, sir, Department of Physics at Dr. V.R. Ambedkar National Institute of Technology, Jalandhar. First and foremost, let me express our deepest gratitude to the Ministry of Education under the Government of India for initiating the global initiative of academic network GIAN, which fosters academic collaboration by bringing together national and international experts. This program enables the sharing of cutting edge knowledge and insights, and we are thrilled to contribute to this initiative through today's course. Environmental radioactivity is a subject of critical importance in today's world, with increasing global attention on sustainable development and environmental protection. Understanding the sources, effects, and management of radioactive materials in our environment is more crucial than ever. This course, led by eminent experts in the field, promises to comprehensively explore this vital topic and equip us with valuable knowledge and tools to address related challenges. In this regard, I warmly welcome the coordinator of this GIAN course, Professor Rohit Mehra, sir. Without the efforts of those who helped this course would not have been possible. At present, Professor Rohit Mehra sir is working as a Dean Research of Consultancy and Professor in Department of Physics at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. He has been active researcher in the field of environmental radioactivity for the past 20 years. He has supervised 19 PhD students and currently supervising 6 PhD students. He has published more than 200 research papers in Journal of International Repute. He has been selected among the world's top 2% of scientists by Stanford University and awarded a medal for his research in this field. I invite Professor Rohit Mehra sir to inaugurate the course officially, welcome our speaker and share words of wisdom with our participants.
So, good morning, all of you, and I formally welcome Professor Tokonami because he has given his consent whenever we approached him to organize this course. So, he has very kindly consented it, and I am very thankful to him because he is always kind to us, to our group also. Because whenever we are doing research since last 20 years, we are doing in collaboration with some of the groups of GNDU, some of the HNB Gadwal University, and even with the Tokonami sir. And we are having some intercomparison activities with the Japanese group also. And I hope that during the tenure of these 5 days, the readers will learn a lot. And we have kept this course in such a fashion that initially Dr. Tokonami will be telling you what are the basics ideas, like how the radon and how the radon isotopes, and they are important for the measurement of environmental radioactivity. And we have designed it in such a fashion that after completion of this course, the participants will learn the basics of environmental radioactivity, the different techniques which are required or used for the measurement of environmental radioactivity, and how it could impact the health risks of the human populations. And I am also thankful to the coordinator of the GIAN, National Coordinator GIAN, my director, my registrar, and along with my team. So who has given me full support for organizing this course. And this is a course, actually, Dr. Tokonami, you might not be knowing the details of this program. The reason is, this is an initiative which has been taken by the government of India to invite some experts in the different areas to deliver lectures either online or offline, so that the human population can get the benefit of their knowledge. So based upon this, people apply for this course, and based upon the biodata of the expert, it has been evaluated by different experts, and your course, this course has been selected. So we are thankful to you that you have given your consent to act as a speaker for this course. Now I would like to hand over the mic to you and would request you to start your proceedings with the first lecture of on the topic of radon isotope. Welcome, Dr. Tokonami.
Thank you very much, sir, for your kind words. We sincerely appreciate your leadership in bringing this remarkable program. We are particularly privileged to have Professor Shinji Tokonami sir, our foreign faculty, with us for this course. Professor Tokonami is globally renowned expert in the field of environmental radioactivity, and his presence here adds immense value to our program. Professor Shinji Tokonami is a professor and director at the Institute of Radiation Emergency Medicine at Hirosaki University, Japan. His research primarily concerns radon, nuclear medicine, radionuclides, radiochemistry, and hydrology. His studies on effective dose are significant aspect of his work in nuclear medicine and are often related to studying air pollutants. He has published more over 500 such articles in esteemed international journals and has 4 patents to his name. I invite our esteemed speaker, Professor Shinji Tokonami, sir, to give his introductory remarks.
Thank you very much again. Thank you for a kind introduction. I'm very honored to be here as a lecturer. So actually, this is the second time for me to join the GIAN training course organized by Indian government. So today, first of all, I would like to start the topic on the fundamentals of radon isotopes. Okay, can we start now? So our institute is located by northern part of Japan. It is snowing so much. The snowfall is more than 1 meter. But in the workplace is very comfortable. So now we start the lecture. Can you see my slide?
Yes, sir, we can see, but you can move it.
Okay.
Yeah.
Okay. The first one, the fundamentals of radon isotopes.
Yeah, they are moving, sir. They are moving. Yeah.
Okay, thank you. According to Jacobi, 1993, the saga is a scientific thriller with tragic futures and political confounders. The historical root of this saga reaches back to the 15th century. It is a field full of dilemma, controversies, and frustrations, some of which still persist. What is radon? Radon is an inert and radioactive rare gas. It is natural and is everywhere. It is continually produced by the decay of uranium-238, which occurs naturally in soils and rocks. Radon is colorless, odorless, and tasteless. Needs special equipment to detect radon. Radon generates a chain of radioactive decay products. All of them are heavy metals. There are 3 isotopes of radon. There is can you see, wait a moment. Can you see laser? Can you see?
Yes, yes.
Yes, sir.
Okay.
Yes, sir.
Thank you. Yeah. So in uranium-238 series, radon is generated with a half-life of 3.82 days. And finally, it become Red-206 as a stable isotope, stable element. Here is a uranium-235. Here is a 219 radon, namely actinium. The half-life is very short, less than 4 seconds. So here is a thorium-232. After several decays, the radon-220 is generated. Namely, here is thorium. The half-life is less than 1 minute. The radon-222 is important because it has a long lifetime and it escaped from the rock because it is gas. And long life of Red-210 becomes a significant background. Radon has a short-lived decay product such as look at this. Polonium-218 with 3 minutes, Lead-214, 27 minutes, Bismuth-214, 19.7 minutes. It is a direct cause of internal exposure due to inhalation. In most cases, thorium is ignored, but in our case, especially Asian countries, we cannot ignore the thorium. Then exposure to actinium is generally very low. Why is radon of concern? Radon is the second cause of lung cancer, the class 1 carcinogen. Radon is responsible for almost one-half of total ionizing radiation doses received by the public each year. The population of lung cancers attributable to radon range from 3 to 14 depending on the average radon concentration in the country. Look at this figure. According to the ANSCIA 2008, the public annual effective dose is a half of the public dose. Effective dose is radon, including toron, 1.26 millisievert per year. Then terrestrial gamma radiation 0.48 millisievert, cosmic radiation 0.39 millisievert per year. The food is 0.29 millisievert per year. As a total, world average annual effective dose is estimated to be 2.4 millisievert per year. Longer exposure gives a greater risk. Higher levels gives a greater risk. Combination with smoking gives a greater risk as well. This slide shows the behavior of radon progeny in an enclosed space such as a mine or a room. See, radon progenies are solid particles. Some of them are charged. They are chemically active and their half-life is less than 30 minutes. See? Most of polonium-218 freshly formed is positively charged, almost 90%. Rest of them are neutral. After radon decay, solid particles of radon progeny are formed. They are called ultrafine progeny or unattached progeny. Most of them are positively charged, as I mentioned. Radon progeny which attach to ambient aerosols are called attached progeny. Both particles deposit on walls or floors with their own diffusive velocity. The unattached progeny has a higher velocity than attached progeny. Radon in environment. Radon can escape from mineral grains and move into the pores between them. From these pore spaces, radon atoms travel through microcracks and tunnel volumes either by diffusion or advection. Once radon reaches the surface, it quickly dilutes to harmless concentration. However, its concentration can build up in poorly ventilated areas such as buildings. Regarding radon pathways to homes, radon enters dwellings through both convection and diffusion. Yeah, look at this. Convection and diffusion. Its filtration is driven by the pressure differential between the building shell and the ground around the foundation, produced by the higher temperatures within the shell. It is called the stack effect. Mechanical ventilation, and to some degree also by wind blowing on the building. The primary source of radon is the soil or rock beneath a home. It can enter through the cracks in solid floors, construction joints, cracks in walls below ground, gaps in suspended concrete or timber floor. Gaps around the service pipes, and cavities in walls, like this way. Other sources of radon is the first one, building materials. Brick concrete and gypsum could contain traces of radium, and therefore they are potential sources of radon. Radon exhales from building materials to indoor environment. The second source is water. Radon can dissolve and accumulate in groundwater sources such as wells in uranium-rich geological areas. Radon in water can be released into the air during a routine water use. The advection process is considered to be the predominant mechanism compared to diffusion. Here is a radon entry rate expressed in becquerel per cubic meter per hour. Wooden house, concrete house, masonry house, building materials by diffusion is 2 to 16. Subjacent soils by diffusion 4 to 14. Advection 20 to 60. Water degassing, almost 1 becquerel per cubic meter per hour. Natural gas, it is around 0.3. Indoor radon concentrations are influenced by soil and geological composition. Radon concentration in soil, soil permeability, building construction, ventilation, weather and climate conditions, and occupant behavior. Radon levels can vary within the building itself, as well as can fluctuate daily and seasonally. I can show you the guidelines for safe radon levels. Recommended radon levels. Guidelines typically establish a recommended reference level for radon concentrations in homes. Action levels. The guidelines often specify action levels that indicate when radon testing and mitigations are necessary. Measuring recommendations. Guidelines offer recommendations for radon measurement, including the method and duration of testing. Mitigation measures. If radon levels exceed action level, guidelines outline the necessary steps for mitigation. Public awareness. Guidelines often emphasize the importance of public awareness and education about radon exposure and its health risks. Here is the international and national guidelines on radon gas. This is the authority, county or region, and guidelines. ICRP, International Commission on Radiation Protection, the ICRP recommends that national authorities establish a national reference level that is as low as reasonably achievable in the range of 100 to 300 becquerel per cubic meter, while considering the prevailing economic and societal conditions. World Health Organization. World Health Organization, WHO, recommends a reference level of 100 becquerel per cubic meter for indoor radon. However, if this level is not achievable, they advise that the radon concentration should not exceed 300 becquerel per cubic meter. According to the International Atomic Energy Agency, namely IAEA, in its International Basic Safety Standards, BSS, the IAEA sets a radon reference level of up to 300 becquerel per cubic meter and recommends national policies to establish an action plan for reducing concentrations of radon in existing and new buildings. European Union adopted Directive 2013-59 Euratom, which mandates that member states establish a national reference level for indoor radon not exceeding 300 becquerel per cubic meter. The directive also requires radon risk assessments in workplaces and living spaces, along with mitigation measures for areas with high radon concentrations. In the United States Environmental Protection Agency, EPA, recommends an action level of 148 becquerel per cubic meter for picocurie per liter for indoor radon in homes. If testing reveals radon levels at or above this level, the EPA advises homeowners to take steps to reduce it. In Canada, Health Canada advises that indoor radon levels should not exceed 200 becquerel per cubic meter, recommending mitigation measures if concentrations are above this threshold to reduce levels accordingly. This table shows the indoor radon concentration in several countries. Here's a country, arithmetic mean, geometric mean, and geometric standard deviation. Normally, radon concentration follows log normal distribution. For example, in Canada, the arithmetic mean of radon concentration is 70 becquerel per cubic meter. In Czech Republic, the arithmetic mean is 118 becquerel per cubic meter. In general, the European countries is radon concentrations in European countries is relatively high compared to other countries. Here is Japan. Japan, the arithmetic mean is 14 becquerel per cubic meter. In the case of United States, the 48 becquerel per cubic meter. This data are based on WHO 2019. The radon mitigation is any process or system used to reduce radon concentrations in buildings. Two different general approaches are available for reducing the level of radon indoors. Reducing the rate at which radon enters from its sources. Increasing the rate of removal of radon from indoor air. Before the mitigation, radon level is quite high, but after mitigation, the radon become the low. Radon level is become low. Okay, I found a question, slide 12. How is radon entry rate via different mechanisms is measured? Here, look at this. Yes, actually, they measure the acceleration rate from the mold, or of course, they calculate the radon concentration indoors and in soil. Then they can estimate the radon entry rate. So ceiling foundation cracks and gaps for these techniques are often used as radon mitigation. Applying sealant to cracks and openings in the foundation walls and floors to prevent radon entry. Like this. Look at this photo. And the effectiveness is moderate. It varies depending on severity of cracks. And the cost is low or moderate, between low and moderate. Subslab depressurization. A pipe system is installed beneath the foundation, namely slab, of the building. This system is connected to the fan that continuously draws air and gases from beneath the slab and vents them outside, usually above the root line. The effectiveness of technique is high. Most effective. I can say it is most effective, but the cost is moderate. Here is a depressurization piping system. It's a kind of chimney. Another technique, people use a sub-membrane depressurization, SMD. Similar to SSD, subslab depressurization, sub-membrane depressurization is used when homes have a cooler space instead of a full basement. A plastic sheet or membrane is placed over the entire soil floor of the cooler crawl space. This membrane is tightly sealed to the walls and any supporting structures to prevent radon gas from entering the indoor air. The effectiveness of this technique is high, very effective, but the cost is very high. The ventilation. Enhance the airflow inside the home to dilute radon levels by opening windows and running exhaust fans. The effectiveness is low, moderate, depending on the ventilation methods. The cost is low. This figure exemplifies the time variation of radon concentration. Well ventilated. This is a closed, the black square means outdoor radon concentration. If the ventilation is worked well, the concentration, indoor concentration reaches outdoor concentration. Despite its negative aspect, such as being a leading cause of lung cancer, radon gas also has positive applications in scientific research and environmental studies. The following properties of radon make it an ideal tracer. Short half-life, inertness, high abundance, 2 to 3 orders of magnitude in groundwater than surface water. Sensitivity to sudden changes in subsurface conditions. Positive aspect, here is positive aspect, atmospheric studies, climatic research, tracer for earthquake studies, tracer for geochemical exploration, geochemical and geophysical tracer in marine system. On the other hand, here are negative aspects, health effect, namely lung cancer. Background in laboratories, that is to say, Super Kamiokande Neutrino Observation Laboratory. Radon as an earthquake precursor. Prior to an earthquake, stress builds up in the rocks surrounding a fault. This stress can cause microfracturing or shifts in rock formations, allowing radon to escape more readily from the subsurface. A sudden spike in radon levels has been observed in some cases before an earthquake, leading scientists to consider radon anomalies as potential precursors. Radon monitoring stations have been established in earthquake-prone regions to track fluctuations in radon levels. Variability in soil composition, groundwater movement, and atmospheric conditions can also impact radon levels, making it challenging to distinguish seismic-induced changes from natural variations. Ulmov and Mabashev observed unusual radon concentration levels in hot mineral water from a deep aquifer, 1,300 to 2,400 meters in the Tashkent Artesian Basin prior to the 1966 Tashkent earthquake. Magnitude is 5.3. Other seismic events of magnitude 3 to 4. Analysis conducted after the earthquake showed that radon concentration had peaked several years prior to the main event, returning to normal levels afterward. A similar pattern was observed in the lead-up to large aftershocks, though through over a short time frame. Here is the first evidence of radon in groundwater as a precursor of earthquake. Regarding Kobe earthquake occurred in Japan, 1995, January 17, magnitude 7.2. The Kobe earthquake of January 17, 1995, magnitude 7.2, which is often taken as an example of the failure of the deterministic forecasting, had been preceded by marked anomalies of radon in water, but since there was no foreshocks activity and the signal was not taken into account, the observation well, located 17 meters deep and 30 kilometers from the epicenter, showed stable radon levels around 20 kilobecquerel per cubic meter at the end of 1993. From October 1994, radon concentrations began to gradually rise, reaching 60 kilobecquerel per cubic meter. On January 7, 1995, 10 days before the earthquake, radon levels spiked sharply, followed a sudden drop on January 10th, just 7 days before the earthquake. The Aquilia earthquake, April 9, 2009, magnitude 6.3. It was based on radon measurement by a technician working in the underground laboratory in the Gran Sasso Tunnel. Here is Italy. The main shock occurred 1 week after Mr. Giuliani had predicted it with an epicenter located just outside of the city, 55 kilometers away from the Salmona. In the case of radon as an atmospheric tracer, the half-life 3.8 days is short enough, allows tracking over short distances without excessive accumulation. Half-life long enough compared to typical turbulent timescales less than 1 hour. The noble gas does not react chemically with other species. Its only sink is by radioactivity K. The radon is a sensitivity indicator of vertical mixing. Radon's concentration gradient with altitude marks its ideal for studying vertical atmospheric mixing. Global, spatial, and temporal variability. Radon's variable levels globally provide insights into an air movement and pollution patterns. Known source, the large gradient in the concentrations of radon between oceanic and terrestrial radon sources aid in identifying the sources of air masses, continental versus maritime. hourly radon time series of typical synoptic scale variability and under conditions of mixed fetch. Observations under persist oceanic fetch as baseline sector. Observation under persistent continental fetch mainland sector. Here the mainland fetch is a clear example of the correlation between the radon concentration and source strength type, continental, island, and marine. Radon as a tracer for monitoring NaPl contamination in groundwater. One of the key properties of radon is that it has high solubility in organic liquid, and hence this property can be utilized for three related applications: residual NaPl contamination in soils, residual NaPl contamination in aquifers, monitoring the effectiveness of remediation of dissolved NaPl in groundwater. Soil radon remains trapped within the NaPls, resulting in a local reduction in the radon concentration within close proximity to the high contaminated area. This graph shows radon activity concentration in the airstream determined during the typical experiment. The arrow indicates the monument of the implementation of the NaPl vessel. Radon as a tracer in the monitoring volcanic activity. There are many active volcanoes in Japan. In particular, the Sakurajima volcano, which is located in southern part of Japan, has been very active since 2009. The phenomenon of increasing outdoor radon 222 concentrations before earthquakes associated with dysautorophism has been reported by many researchers. Radon exhalation rate from soil surface was measured together with meteorological data in order to discuss the possibility of the prediction of volcanic activity. This here is Sakurajima, in southern part of Japan, with the picture of Sakurajima. It is still active. This graph shows the number of eruptions in Sakurajima volcano. Here is a number of eruptions and the Western calendar here. The radon exhalation rate showed its maximum value after rainfall. The daily variation of the radon exhalation rate and carbon dioxide concentration in the accumulation chamber seems to be in good agreement. Thus, radon will become a good tracer for carbon dioxide monitoring in environment. It is necessary to develop a correction method for the effect of rainfall on the radon exhalation rate obtained by the flow-through method. I'll explain this technique later. Here is a radon exhalation rate, and you can see the influence of rainfall. This is a precipitation. Here is a carbon dioxide flux. Here is a number of volcanic earthquake. The background radon exhalation rate was 6 plus minus 3 millibecquerel per cubic square meter per second. As a summary, radon is a colorless, the odorless, and tasteless gas which makes it undetectable by human senses. Exposure to radon is the second leading cause of lung cancer following smoking. The primary source of indoor radon is soil, and it can seep into homes through various entry points such as cracks in foundations, walls, and floors. Despite its harmful effects, radon also has certain applications. As I can say, radon is an visual environmental hazard, but with proper awareness, measurement, and mitigation, its health risks can be minimized. Dr. Mehra, my first lecture is done.
Thank you very much, sir.
Thank you very much, sir. It has been a fascinating talk. If there is any question from the audience, then please ask. Now it's another hour before our following lecture on fundamentals of radon by Professor Shinji Tokonami sir. Respected sir, I invite you to share your valuable knowledge on fundamentals of radon in continuity with the first lecture.
Hello.
Hello?
Hello. I'm audible, sir?
Yes? Huh?
Hello.
Hello?
Am I audible, sir? Sir, there is a question from one of our participants. Sir, in slide number 2, how is the radon entry rate measured via different mechanisms?
Yes. Yeah, this one.
Yes, sir.
Okay. So, in order to estimate the radon entry rate, we can measure the indoor radon concentration and radon concentration in soil. We can calculate. Also, in some cases, we can measure the acceleration rate, surface acceleration rate. Do you understand what I mean?
Yes, sir. Thank you very much, sir.
Yes.
Sir, there are no more questions from the participants, so we can start our next lecture.
Okay. Maybe we can not fundamental, but this topic is measurement techniques, but it contains many fundamentals. So it takes more time to complete this lecture. Okay, let me start. Tracking the individual in visual threat. Radon detection techniques for health and safety. As repeated in visual and odorless, radon is a radioactive gas that cannot be detected without specialized measurement techniques. Health risks. Long-term exposure to elevated radon levels is the second leading cause of lung cancer. Regional variability. Radon levels can vary significantly by location, so measuring radon is crucial to assessing and mitigating risks in different areas. Effective mitigation requires accurate detection. Only through precious radon measurement can effective mitigation strategies be implemented to reduce exposure. Public awareness and safety. Radon measurement techniques are key to raising awareness about radon risks through accurate data. I'll show you the unit definitions or quantities. The historical units we have historical units of exposure. In the United States, they use picocurie per liter. This is old unit. 1 picocurie per liter equals 37 becquerel per cubic meter. Here is a special unit, working level. One working level represents many combinations of short-lived radon decay products in 1 liter of air that will result in the ultimate emissions of 1.3 times 10 to 5th MeV of potential alpha energy. Working level mass, WLM, referring to exposure to 1 working level for a working month of 170 hours. This unit, working level month, is commonly used in uranium mines for radiological protection. Here's the activity. The number Tm of spontaneous nuclear transition or nuclear disintegration of a radionuclides of amount n produced during a short time interval dt. The unit activity is becquerel. The activity concentration. Activity A per unit volume V of the respective isotope. The unit of activity concentration is becquerel per cubic meter. Potential alpha energy, PAE, the potential alpha energy of a single atom of a short-lived radon progeny radionuclide is the total alpha energy emitted during the decay of this atom, but not including the relatively long-lived radionuclides led to 10. Here is the potential alpha energy derived from polonium-218. The potential alpha energy is a quantity of characterizing radon progeny atmospheres, not radon atmospheres. It can be written by this equation. This is atom concentration. Here's the energy. N is the number of respective atoms used for theoretical work. The unit potential alpha energy is Joule. Potential alpha energy concentration, PAEC. The potential alpha energy concentration of any mixture of short-lived radon daughters in air is the sum of the potential alpha energy of all short-lived daughter atoms present per unit volume of air. PAEC can be written like this. This is activity concentration. This unit, PAEC expressed in joule per cubic meter or MeV per liter, and working level. One working level equals 1.3 times 10 to the 5th MeV per liter, which is equivalent to 2.08 times 10 to minus 5th joule per cubic meter. So here is a practice. Convert one working level to potential alpha energy concentration for radon progeny, PAEC expressed in MeV per liter and joule per cubic meter respectively. Note that the following information will be available accordingly. Okay, this is a practice, but you see, you can find the answer here. But I suggest you should calculate PAEC independently. Exposure to radon, the time integral of the activity concentration during the defined period of time is a time integrated concentration. The unit of exposure to radon is becquerel per cubic meter hour. Potential alpha energy exposure, the time integral of the potential alpha energy concentration in air Cp over a given time period, delta T. The unit of potential alpha energy exposure is joule per cubic meter hour. Regarding equilibrium factor, in practice, radon and its progeny will rarely be in equilibrium. Equilibrium factor characterizes the disequilibrium between radon gas and its progeny. The equilibrium factor can vary from 0 to 1. There is a negative correlation between equilibrium factor and ventilation rate. For example, indoor environment, equilibrium factor is around 0.4 by natural ventilation. In mines, equilibrium factor is about 0.2 by forced ventilation. This is a sample of individual concentrations of radon and radon progeny. Look at this. So we use equivalent concentration, EEC, very often. EEC, equilibrium equivalent concentration, is an alternative to using PAEC. Equilibrium equivalent concentration is the concentration of radon in equilibrium with its progeny that would give the same PAEC as the actual non-equilibrium mixture. If the radon concentration is known, the EEC can be estimated like this way. This EEC equals concentration of radon times equilibrium factor. If the concentration of the individual radon decay product is known, the following equation can be used to determine the EEC. Look at this. So there is this practice. Air contains the following radionuclides: radon concentration 70 becquerel per cubic meter, unattached radon progeny concentration 10 becquerel per cubic meter, 3 becquerel per cubic meter, and 1 becquerel per cubic meter. Attached radon progeny concentrations is 40 becquerel per cubic meter, 25 becquerel per cubic meter, and 15 becquerel per cubic meter. What are the equivalent radon concentration, EERC, unattached fraction, FP, and equilibrium factor. Before this working on the practice, I have to explain the attached fraction and unattached fraction. Attached fraction, after radon solid progeny generation, radioactive aerosols are formed in two steps, unattached fraction and attached fraction. Got this? The sum of attached and unattached fractions is equal to 1. The fraction of the potential alpha energy concentration of short-lived radon progeny that is attached to the ambient aerosol particles. So nucleation mode particle activity median diameter varies between 10 and 100 nanometers. Accumulation modes AMD varies between 100 and 450 nanometers, and cosmode particles AMD more than 1 microns. This is micron. Unattached fraction, FP, a fraction of progeny may not become attached to ambient particles, and its quantity is often referred to as the free and unattached fraction. The unattached fraction is defined as a fraction of the potential alpha energy concentrations of short-lived radon progeny that is not attached to the ambient aerosol. Calculated using the following equation. FP equals unattached EEC over total EEC. The range of unattached fraction is observed 0.05 to 0.15 without aerosol sources, less than 0.05 with aerosol sources such as smoking, cooking, and stove heating. Then, okay. So once again, air contains the following radionuclides: radon concentration 70 and attached radon progeny concentrations: polonium-218, lead-214, bismuth-214, 10, 3, and 1. Attached radon progeny concentrations: polonium-218, lead-214, bismuth-214, 40, 25, and 15. Then we will calculate the equivalent radon concentrations and unattached fraction and equilibrium factor. You can see EERC 0.16 times this unattached polonium-218 activity concentration plus 40. This is attached polonium-218 activity concentration. And here, this is unattached and attached. For here is a lead-214 and bismuth-214 is here. One is unattached and attached. Then we obtained 25.76 becquerel per cubic meter. Then, in the case of unattached fraction, we can calculate like this way. This is total EERC. And here is unattached EERC. 10, 3, and 1. Then unattached fraction was 0.116. After that, we can calculate equilibrium factor. We can calculate like this way, 25.76 over 70. The result is 0.368. The measurement techniques. Classification of detection. Detection methods, direct method, and indirect method. Alpha particle detection, a scintillation detector, gas field detector, solid state nuclear track detector. Alpha detection, semiconductor detector, solid state track detector, nuclear track detector, beta particle detection, scintillation detector, gamma ray detection, semiconductor detector, and scintillation detector. Here are objectives of measurement. Long-term indoor and wait a moment. Sorry. Long-term indoor radon and radon progeny assessment. Short-lived indoor radon screening. Identifying success or failure of preventive remedial measures. Those assessments based on radon and its progeny concentrations. Risk communication. Epidemiological investigations of the health impact of radon exposure, and scientific research. Classification of time resolution, graph sampling technique. The radioactive content of discrete samples of an air taken over a short term at a single point is analyzed. In the case of continuous technique, this technique is designed to provide information on the time dependence of concentrations. In the case of integrating technique, it provides a single concentration determination, generally averaged over a period of a few days to a year. I can show you the international standard of radon methodology. ISO provides radon standardized technique methodology on radon 11665. This, for example, the measurement of decay products, ISO provides two standards. ISO 116652 contains integrated measurement techniques. ISO 11665 Part 3 gives a spot measurement. In other words, this is a grab sampling, small intermittent measurement. In the case of radon, part 4 gives an integrated measurement. Part 5, continuous measurement. Part 6, spot measurement. Here is the application. Part 7 provides accumulation method for estimating surface acceleration rate. Part 8, methodologies for initial and additional investigations in buildings. Part 9 gives test methods for acceleration rate of building materials. Part 11, test methods for soil gas with sampling at depths. Here is the classification of collection method. Collection method of radon gas is classified into two methods. One is passive method. No power supply, integral exposure experiment. This technique is suitable for integral exposure measurement. This technique needs analysis after exposure using special equipment, track edge, activated charcoal, and electrolyte. In the case of active devices, active methods, electric power required. Wait a moment. Thank you for waiting. Electric power, in the case of active devices, electric power is required. It can store the time distribution of radon concentration. And we can get the direct data. For instance, silicon detector with high voltage chamber and alpha spectroscopy, ionization chamber, and scintillation cell. Here is an example of active devices. Here's this device is based on the electrostatic collection method. This is commonly used alpha gun based on pulse type ionization chamber. There are many types of radon monitors. Ionization chamber, ionizing energy of air about 34 electron volts per charge carrier. One alpha with 3.5 MeV energy result in about 10 to 5th charge carriers. In other words, ion pairs. Ionization chamber is well known and recognized as a standard equipment in order to calibrate other detectors. This ionization chamber is used as a primary device. As their characteristics the volume, inner volume is 1 to 15. Someone raising a hand.
Hello, Supriya ma'am.
Hello?
Hello, Supriya ma'am. If there is any question from your side. Sir, you may continue, sir.
Okay. Thanks. The inner volume is generally 1 to 1.5 liter, made of stainless steel. The larger the volume, the higher the sensitivity. If you choose a larger volume, you can get high sensitivity. So here is a commercial product of ionization chamber, namely alpha-GAD. Alpha-GAD uses a pulse ionization chamber filled with an ambient air. Here's alpha-GAD. Alpha particles produce many ion pairs as they move through the gas, with the number of pairs being proportional to the energy lost by the alpha particles. Signals the primary alpha decay of radon plus subsequent polonium-8 decay. Got this. Here's a electrolyte, and outer gas, outside air go through, enter the chamber through the fiberglass filter. This device can select airflow mode and diffusion mode. Measurable range is 2 to 2 million becquerel per cubic meter. Minimum detectable level is less than 2 becquerel per cubic meter. Efficiency 1 CPM at 20 becquerel per cubic meter. Diffusion and flow mode. We can choose the diffusion mode and flow mode. And this monitor also can measure the relative humidity, temperature, and atmospheric pressure. As a drawback, background from polonium-210 increases over the lifetime of the instrument. This is another type of ionization chamber, namely Atmos, made in Sweden. The principle, 2.2 liter pulse height chamber. Measurable range 1 to 10,000. 100,000 becquerel per cubic meter. Measurement precision 10% at 800 becquerel per cubic meter and measuring time. Minimum detectable activity 5 seconds at 180, 1,800 becquerel per cubic meter. 1 minute at 150 becquerel per cubic meter. 1 hour at 2 becquerel per cubic meter. Air humidity above 10 gram per cubic meter can affect the measurement result. Regarding scintillation cell, it is most useful device for radon measurement. Therefore, it is used as a secondary device. It is often called Lucas chamber, Lucas cell. As the characteristics, the inner volume is 100 to 300 milliliter. Easy to handle, and the inner wall is painted with zinc sulfide scintillator. But energy discrimination is not possible. The typical counting efficiency is estimated to be 75 to 80%. Here is a commercial product of scintillation cell, Pylon 600A and AB7. This is a counting device. AB7 characteristics, active and passive scintillation cells are available. Maximum counting rate at 10,000 CPS. Electronic background less than 0.4 CPM. Pylon 600A characteristics, alpha energy range 4.5 to 9 MeV. Lowest activity detectable concentration is 27 becquerel per cubic meter. Sensitivity of this cell is 0.037 CPM per becquerel per cubic meter. Photomultipliers are sensitive to vibration and mechanical shock exposure to direct light and dislocation. The next is an electrostatic correction method. Commercial product name is Rad7. Radon and toron are allowed in while their progeny are blocked. Radon decays to charged polonium-218, as I mentioned in the previous slide. Polonium-218 collected on a silicon semiconductor detector using an electric field. In the case of Rad7, 2200 volts are imposed. Radon concentration calculated by sniff mode, rate of decay of polonium-218 in A window, normal mode, rate to decay of polonium-218 plus polonium-214 in the A and C windows. This is an example of alpha spectrum collected on the surface of silicon semiconductor detector. This is a background, polonium-210. Polonium-218 and lead-214 are used for calculation of estimation of radon concentration. On the other hand, polonium-216 and polonium-212 are used for toron measurement. Simultaneous independent measurement of radon and toron can be done. Normal sniff mode sensitivity is normal mode 13 CPM per kilobecquerel per cubic meter. Cynic mode activity 6.7 CPM per kilobecquerel per cubic meter. Intrinsic background 0.2 becquerel per cubic meter for lifetime of the instrument. It is dependent of changing humidity. This is the drawback of this technique, because positively charged radon progeny are neutralized by vapor, water in air. That's why if you use the radon 7 in humid environment, you get the lower sensitivity. Therefore, we use this drying agent, a discant. Alpha track edge detector. Alpha particles from the decay of radon and its progeny creates a track in the material. Tracks will be revealed through etching with hydroxide, sodium hydroxide, and potassium hydroxide. Number of tracks are proportional to radon exposure. This technique is simple to use, relatively inexpensive. Long exposure time is necessary. It is suitable for determining annual average concentrations. This track detector provides a single measure that indicates the integrated exposure. The left side shows the LR115, cellulose nitrate. The right side, CR39, polyaryl diglycol carbonate. I know Indian colleagues use this track detector. Advantage of this track detector: inexpensive, insensitive in EM, robust, and can be cut into small pieces. Their disadvantages are not reusable. Counting is time consuming by manual counting. We can get a shorter time using commercial digital system, but it is very expensive. This slide shows the bare or open detector configuration. Here is the simplest technique. Alpha track detectors are open-faced with no filter or barrier for radon decay products. Tracks are formed by alpha particles originating from both radon and thoron and their decay products. Sensitive to radon decay product plate out on the detector surface. This technique provides assumed radon concentration, but it is not accurate. This figure, this is a French detector. Regarding closed configuration, it is often called cup method. The filter or barrier is used to prevent the radon decay product from entering the sensitive volume of the devices. The measurement result is not affected by the presence of radon progeny in indoor air. There are several types of passive radon detectors with a cup type. I can exemplify the German passive radon detector. There is no discriminative measurement between radon and thoron. The polycarbonate foil film is used as a detecting material. Here is a large area glass fiber filter, which results in the large air exchange rate. And this is a plastic body. We are concerned with heterogeneous deposition in the inner wall. This figure shows a control of ventilation rate in radon monitor. Here is a radon monitor. If the radon monitor has a high ventilation rate, large ventilation rate, radon and thoron, both isotopes can enter inside of the monitor. On the other hand, if the monitor has small air ventilation rate, only radon can go into the chamber, into the monitor, because the thoron, half-life of thoron is much shorter than radon, less than 1 minute. Thoron, in this monitor, thoron travels with a long time. It decays before entering the inside. So I can explain the passive radon thoron discriminative monitor. Namely, Radioactivity. Radioactivity was collaboratively developed by NIRS, this is my previous workplace, and Radosys company in Hungary. The shape is cylindrical, the inner volume is 30 milliliter, quite small. We use CR39 as a detecting material. We set 2 detectors used with different air exchange rates. Then we can eliminate the thoron interference in radon measurements. The body material is electroconductive plastic. Here. The CR39 is placed at the bottom of monitor. And here is a holes covered with electroconductive sponge. Physical strength was enhanced by use of electroconductive sponge instead of paper filter. Maximum detectable concentration is 8,000 becquerel per km. Here is the limit of detection. In the case of radon, LOD is estimated to be 3 becquerel per cubic meter. In the case of thorium, it is estimated to be 14 becquerel per cubic meter. I will explain the charcoal adsorption method. Short-term measurements of indoor radon, optimally 1 to 7 days. Charcoal functions as a collector rather than a detector. Radon can bind to charcoal via van der Waals interaction. After radon is trapped. A proper detector measures radiation from radon and its progeny. Charcoal is reusable by heating. Charcoal is also a very good absorber of water vapor, which can reduce the adsorption efficiency for radon. Here is a sample of charcoal canister. It contains activated carbon with silica gel here. And this is cylindrical vessel. So we are moving on to the radon progeny measurement techniques. First, classification of detection. We can classify two methods, cross-counting method, the other one, spectroscopic method. Alpha particles emitted from polonium-218 and polonium-214 are counted without energy discrimination. Normally, in this technique, we use the zinc sulfide detectors, scintillation detectors. In the case of spectroscopic method, the alpha particles in specific regions are counted, where energy is discriminated according to each radionuclide. Generally, silicon semiconductor detectors are used in this method. I can show you the commercial product of radon progeny monitors. This is the active type, alpha PM. The company is the same as AlphaGrad. This is a Pylon WLX. Here's an alpha nuclear. This is a Tracer Lab BWLM plus S. Here's the Dozman Pro. All the monitors use the silicon semiconductor detector. This is a radon measurement technique, but actually, this technique used for radon gas measurement. We call two-filter method. There are two filters, upstream and downstream. This is a vessel, decay chamber. Only radon is gas, but radon progenies are solid particles. Radon progeny cannot enter inside. Only radon gas go inside. Then radon decays. The And after that, radon progeny are formed and collected on the downstream filter. So we place the semiconductor detector here. We get the radon progeny alpha energy spectrum like this way. Using these counting data, we can estimate the radon concentration. Measurement of individual radon concentrations, usable filters. I can introduce membrane filters and glass fiber filters. Membrane filters are widely used. They have a higher than 99 retention of submicron particles. Aerosols are deposited on the filter surface, minimizing the adsorption of alpha particles. In the case of glass fiber filters, they are equally efficient as collectors, but most of them have small problem with self-adsorption. So the important point is that pore size and material, surface collection efficiency, which filter is the best. We use this index. Also, airflow compatibility and sampling duration. This is a typical sampling arrangement for radon progeny measurement. Components. Here are the components: open-faced filter holder and proper filter, flow meter, and vacuum pump. This is a basic sampling arrangement for radon progeny. Parameters have to be recorded. That they are sampling time, sampling flow rate, which should be calibrated. Transfer time, because polonium-218 has a very short half-life. That's about 3 minutes. So we have to hurry up to transfer from the sampling to measurement. Dr. Mera, maybe I can stop it now. I will accept some questions. Doctor, are there any questions? I will close my talk today.
Thank you so much, sir, for your talk. Is there any question from audience side? Is there any questions? Sir, there is a one question.
Yes. Ah,
So it is, what should be the typical value of unattached fraction of radon progeny in indoor environments?
okay. Actually, in indoor environments, typical value of unattached fraction is around 0.05, just 5%. For if the air is very clean, the unattached fraction goes up to 0.2 or 0.3. Normally, the typical value is 0.5. It's fine.
Okay, thank you, sir. Thank you, sir, very much. It was really an extraordinary session for all our participants. This marks the end of first session of the day. Professor Rohit Mehra lectures will start at 1:30 p.m. IST and 6 p.m. JST. Thank you very much for your patience. We will meet on the same platform with the same Google Meet link at 1:30 p.m. Okay, thank you, everyone.
Thank you.
Okay.
Thank you.
Thank you.
Thank you for the exercise, knowledgeable lecture.
Hello. Sir, can you please repeat your question? Hello.
Am I audible?
Yes, sir, you are audible, sir. So good
Yeah,
afternoon,
yes, sir,
everyone.
yes, sir.
I invite you and I welcome you all in the second session of this GIAN course. The speaker for our this second session is Professor Rohit Mehra, sir. At present, Professor Rohit Mehra, sir, is working as Dean of Research and Consultancy and Department and Professor in Department of Physics at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. And he is currently heading the Radiation Monitoring and Assessment Lab in Department of Physics at NIT Jalandhar. He has been an active researcher in field of environmental radioactivity for past 20 years. He has supervised 19 PhD students and currently supervising 6 PhD students. He has published more than 200 research papers in journals of international repute, and he has been selected as among the top 2% scientists of the world by Stanford University. Rohit Mehra pioneering research and dedication to advancing knowledge in environmental radioactivity is a source of inspiration for all of us. I invite Professor Rohit Mehra to deliver the talk on measurement of natural radioactivity and its impact on human health.
So, thank you, Abhishek, and thanks for the nice introduction. I think we have already concluded this introduction portion in the inaugural session. So, from the tomorrow onwards, there will not be any further introductions of the speaker because we are the only two speakers, Dr. Tokonami, which you have already interacted. Am I audible now? Am I audible?
Yes, sir, yes.
Yeah.
Yes, sir.
So, Dr. Tokonami has given you an idea about the radon and its isotopes and its measurement techniques. So, today I will be giving you a very basic idea that what is natural radioactivity, because we will be planning this course during the tenure of 5 days in such a fashion that after the 5th day you are basically having an expertise in what are the different techniques which are available for the measurement of natural radioactivity and how this radioactivity could impact the human beings, why it is important to study the natural radioactivity in the environment. So with the advent of radioactivity, you could say, if you just start, this slide gives you a basic idea that as he is the Benjamin Franklin is a person who basically invented this technique in such a fashion that lightning was electricity by the kite, and during a keystorm he invented the glass also. And based upon this, Benjamin Franklin was the only person whose picture was published on the dollar, United States dollar currency. So he says basically life is a tragedy that we get old too soon and wise too late. So the basic idea behind this is like we learn so many things in our environment, but we understand those things at a very later stage. So that is why once we start this career as a environmentalist or a nuclear physicist or a person who is dealing with the environmental radioactivity, you should have a basic idea that what we are going to measure, why we are going to measure, and how we are going to measure. Because as a expert or as a scientist or as a researcher, you cannot measure whole of the natural radioactive elements with a single technique. So you require different techniques for measurement of different types of radioactive materials, sometimes in air, sometimes in water, sometimes in soil. Like in the morning, Dr. Tokonami has discussed so many things about the radon. So why radon is important, he has already discussed, because once we say we are going to measure a gas or a material which is in a gaseous state, that is always uncontrollable. Because once it is an inert gas, which is a decay product of radium 226, once from the 226 radium, this alpha particle is emitted out, radon is generated, and radon is in a gaseous state. So once it is a gaseous state, it is uncontrollable. So these were the few facts which were about the Benjamin Franklin. So which I just want to introduce you, because he never presented or patented or any innovation, but still he was very kind enough to deal with the phenomena where we could say that he was capable to understand the problem. So not only the scientists who are important, it is the basic understanding is very important. So that is why I was very much interested in presenting you these 2 or 3 slides of Benjamin Franklin, to make you people aware that though you are working or you are not working in a particular area of a natural radioactivity, but as a science student, as a science graduate, as a human being, you should have an idea to understand that how you are being exposed or why you are being exposed, and once you have been exposed, what type of effect your body could have. To start with, radioactivity, it was discovered very early in 1896 by the famous scientist E.H. Becquerel, so who was working on some of the uranium salts. So once he was working on with the uranium salts, were having a photographic plate, he said that they were uranium salts were affecting some of the photographic plate. This is a very important phenomena which you might have studied in your graduate classes. Now, the basic idea of this presentation will be the introduction to the radioactivity and its health risk, then assessment of radon and thoron in air, assessment of radon in water, assessment of uranium in water, assessment of radionuclides in soil, assessments of heavy metals in soil and water. And I would request you people that not to restrict yourself to the listener mode only. You can always ask, or you could always discuss the things if you are interested that why it is so, even during the talk. And during the tenure of this course, we will be planning in such a fashion that at the 5th day we are having a small quiz type of test for you people also, that how you have understood the radioactivity, and based upon your understanding you could answer that very minor quiz, which is a very normal type of a quiz, which is equally important for a layman, so who is not working in the nuclear physics only, but he is a person who is dealing with some of the radioactive materials. Like you go for medical diagnostics, you have undergone an x-ray. Have you ever asked that how much radiation exposure has been given to me? Nobody asks. In India especially, nobody asks. If you go for a CT scan, if you go for a PET scan, no doctor, no radiologist give you an idea that you have been exposed to this much of radiations. So these are the artificial radiations or the medical radiations, apart from the natural radiations which you are under the influence. So the combined effect of internal, natural, as well as anthropogenic, or you could say artificial, gives you a total dose. So that is why understanding of natural sources is very important, because natural is which we cannot avoid. So like if you are sitting in the room has a different type of environmental factors. One is the air inside the room, second is the ventilation conditions, third is the your relative humidity. So all of these parameters play an important role. And apart from this, the type of choice of building materials in the room also plays a very important for your exposure. So it is very important to understand that how we are going to get the information about the natural sources as well as the anthropogenic sources, that is due to the human activities. So if you just divide the radiation, it is basically of 2 types. One is the natural sources, which we generally call the cosmic radiation, terrestrial radiations, internal sources, and another are the anthropogenic sources, that is due to the human activities. One may be the medical sources, then consumer products which you are using, they may also give you exposure to the natural radiations. Then there are some industrial sources which can also give you exposure. So it is very important to understand that how much we are under the influence of natural sources, how much we are under the influence of anthropogenic sources. Now, if you talk about the radioactivity, it is not a new thing. It was present since last so many years, like from the mother earth. The age of the earth is the same as the half-life of the uranium. So if we divide the radioactivity or radioactive material, we are generally dealing with alpha, beta and gamma rays. And this slides give you an idea that how alpha, beta, gamma, and fourth one we have kept as a neutron. Though neutrons are not directly radioactive in nature, but once the neutrons fall on some of the materials, they cause alpha, beta and gamma to come out. So that is why we have categorized it to 4 categories. And if you see this figure, the alphas could be stopped by a thin sheet of paper. Similarly, the beta could penetrate through the paper, but they can be stopped by thin metal sheets. And similarly, the gammas, they have more penetration power and they could be stopped by the thick lead or steel plates. And finally, the neutrons, they are highly penetrating and we generally use the paraffin wax or water or concrete to stop the neutrons. Now, if you see from this figure, one could have an idea that if we are wearing some clothes, so we are not exposed to the alpha radiations. Okay, it's good enough. By seeing this figure, you could see that it could be stopped by a thin sheet of paper. So my clothes could stop the alpha sources. So it is very much right. But suppose you inhale an alpha source with your breathe. So once you breathe, if you inhale an alpha source, it can enter your lungs. So if it cannot go inside from outside environment, so it cannot come outside from inside environment also. So means if you have inhaled an alpha sources during breathing process, so that alpha will enter into your lungs and will release its energy within the internal lining of your lungs, like on the thin sheet of paper. Now, if you see all these 4 alpha, beta and gamma and neutron, and suppose you are having the same energy for all the parameters, like alpha is say, for example, 2 MeV, beta is also 2 MeV, gamma is also 2 MeV and neutron is also 2 MeV. Now, from this figure, you could imagine that the 2 MeV of energy will be released on the thin sheet of paper in the first case. And in the second case, out of the 2 MeV, some of the energy will be released on thin sheet of paper and rest will penetrate and then it will be stored by the thin metal sheet in the second case. Now in the third case, if you see this cursor, you could see in the third case, same 2 MeV energy is released on, a part is released on the thin sheet of paper, a part is released on the thin metal sheet, and then final remaining energy is released on the thick lead or steel plates. Now by seeing this, you could imagine that for same type of energy, the damage caused by alpha is the highest. Because for same energy of say for example 2 MeV which we were discussing, the maximum release of 2 MeV is in the case of alpha. So the reason is the alpha has the highest ionization power. So that is why alpha sources are very important to study. The reason being they have the highest ionization power and they can release their energy within a particular area on which they strike. So if you have inhaled an alpha sources like radon, which Dr. Tokonami was telling you about radon and its isotope, and the thoron also in the morning, they all are the alpha sources, alpha emitters. So if you inhale those sources which are present in the natural environment, so that release of alpha within the internal lining of your lungs, because you have inhaled it, could damage the internal lining of your lungs. So that is why the study of alpha sources is very important, as they have a high ionization effect as compared to the beta and gamma. And second thing is, the naturally available source of radiation, that is radon, is a alpha source. So now sometimes this is a very basic figure which we generally, it is prepared by one of my student, Dr. Sarabjot. So we generally prefer these type of figures to make you people understand that though you are not a man from a particular radiation field, you could understand why we use the different sources. Sometimes we say it is Becquerel, sometimes we say it is Gray, sometimes we say it is civet. So you could imagine from this figure that if you are only measuring the natural radioactivity, that is the disintegrations per second, so it is measured in terms of becquerels. So becquerels in the sense, that is the number of disintegrations per second. Suppose the natural radioactivity present in a particular area or a room. So it is measured in terms of becquerels, that is the number of disintegrations per second. Now suppose a passenger has a nap beneath that tree on which the apples were falling. So from seeing this, you could imagine that the green apples shown in the figure are the apples who are having impact on that passenger who is having a nap beneath that tree. So that means he is absorbing out of the disintegration only the green color apples. So these absorbed doses are measured in terms of gray. And then the impact of these absorbed doses is the hump which is created. Though hump will not be created with the apples, but just for your imagination, a hump, that is the effect which is being created by the absorbed dose, is called effective dose, and that is measured in terms of civets. So this is the idea behind this, that why we use different sources, Becquerel, Gray or civets, for different types of exposures. So if it is a disintegrations per second, maybe a room might be having a very high level of disintegration per second, but if I don't enter into that room, I will not absorb anything. So once I say I have absorbed it, it is a gray in terms of measured in terms of gray, that is my absorbed doses. And once I say it is the impact of my absorbed doses, that is in terms of civets, that is effective doses. Now comes why we study the radiations. Means what is the reason why we study those radiations? Now in the morning, Dr. Tokonami has discussed a lot of things about the radon, why we study radon, because it is an alpha emitter. So here it is the same type of a figure which I am showing you, that out of this total contribution, including the man-made and the natural and the medical or the nuclear, everything, 55% contribution is only due to the radon. So nearly 82% contribution is from the natural sources and around 18% concentration is from the man-made sources. So which includes the medical, X-ray, nuclear medicines, consumer products. And out of this total 100%, nearly 55% contribution is only due to one source, that is radon. So that is why the study of radon is very important. So these radiations, though they are invisible, but they are very important, they are very dangerous if they have been exposed or if they have been absorbed at a rate more than the recommended action levels. So the average action level recommended for different radiations is different, and if you have exposure more than those recommended action levels, so it is always considered as dangerous. Now, if you see from the figure on the right hand side, that what is the effect, because if you see exposure is in terms of millisievert, because it is the effective dose which we are calculating, that is in terms of sieverts, that is how much the damage has been caused by the absorbed doses. So which we are measuring in terms of sieverts. Sievert is a very bigger unit, so we generally use a small unit, that is the millisievert or microsieverts. So if you see from the figure, an exposure of around 50 to 100 millisievert can change the blood chemistry, and exposure of around 500 millisieverts can cause you the nausea. And impact could be measured within hours. So if you have been exposed to this much of radiation, say 500 millisieverts, within hours you will have a nausea type of a feeling. And if you have more exposure, you could feel the vomiting, hair losses, diarrhea, hemorrhage. And then if the exposure is around 1000 sievert, so impact could be the death of the person also. But these are very bigger units. Naturally, you are not exposed to these much of radiations. You are very limited to very small value of natural exposure, which we will discuss. So around 2.5 millisievert you are being exposed, and out of this nearly 1.5 is the contribution from the radon itself. So that is 55% contribution of the natural. Now, there are some important techniques to measure the radionuclides and heavy metals. And here I am presenting the basic idea of those techniques. That details we will be discussing in our next lecture. This is just a beginning of the course where we could give you an idea that what we are interested in. So we are interested in measuring the radon and thoron in air. Thoron, why it is important, Dr. Tokonami in the morning has explained in detail that the thorium series is also very important, and thoron is a decay product of thoron, and it is very volatile also. So that is why its study is very important, because it can have a different type of impact. And secondly, the alpha particles emitted by thoron, they are having quite big energy. So that is why their study is very important. And then we study the natural radioactivity in soil in terms of uranium, radium, thorium, and potassium. And for these measurements, we generally prefer different techniques which are mentioned here. One is the fission track registration technique. Another is the gamma ray spectroscopy. That is, we could use high purity germanium detectors also, and we could use sodium iodide detectors as a scintillation counter also for the measurement of uranium, radium, thorium, and potassium in soils. We can also study the uranium in waters, and this instrument which is shown here is a LED fluorimeter. But we could have very advanced techniques also apart from this LED fluorimeter, that is the ICP-MS, induced coupled plasma mass spectrometry, and where even with the help of a AAS, atomic absorption spectrometer, you could measure the uranium in water. And similarly, the other heavy metals you could measure in the different water or soil samples, which are these are the two detectors which are available in our lab. One is the atomic absorption spectrometer. This is on the left side, and this is ICP-MS, induced coupled plasma mass spectrometer. So where we could measure the heavy metals in soil as well as in water. Basically, both the instruments work on the liquid samples, but for soil samples, we have to use a microwave digester to digest those soil samples and finally make them in a liquid form, and then we could use those samples for the estimation of the heavy metals in those water samples. Now, this is a very important technique which is used for the measurement of radon and thoron and its progeny. Progeny, you could say, is a daughter product. So it is because radon is 55% contributor in the environment. So it is very important to study the radon as well as the thoron and their daughter products. So this is the technique which is being developed by the BRC, Baba Atomic Research Center, and it is very widely acceptable nowadays. Especially in the Indian environment, they have calibrated it in such a fashion that we are using two detectors within this pinhole cup dosimeters. And if you see from the figure, this pinhole cup dosimeter, there are two red color tapes which are there. So this is a detector which is a cellulose nitrate detector. Presently, its manufacturing has been ceased. We are working on some other detectors also, CR39 and another cellulose nitrate films, which are sensitive for the energy emitted by the alpha particle of radon and thoron. So generally, these detector has a sensitivity value of the order of 4.5 to 5 MeV, and the alpha particles emitted by the radon as well as the thoron, and if you allow the distance of around say 4 or 5 centimeter to travel, and if that alpha particle of around 8 MeV or 7 MeV travels a distance of 4 or 5 centimeter as per the Bragg's curve, it comes into the energy range of the sensitivity of this detector. And once it strikes this detector, it gives a track, that is an damage which is being caused by that alpha particle on this material. So this damage is called the track, and there is a very famous book, especially for the beginners. I would recommend that they should understand the basic physics of track formulation, and Walker, Fletcher and Price book is there, which gives you a very basic idea that how the energy, once it strikes the material, how a track or a damage is caused, and how to measure those damages. Now we are having some advanced techniques. We are having some spark counters which can measure those damages within minutes. But previously, when we were pursuing our research 10 years or 15 years back, so we were counting those tracks or damages with the help of our optical microscopes. So around 400 magnification microscopes which we were using, and then we were counting the damages. And then by applying some of the formulas or comparative techniques, we could understand that this damage is causing this much of damage is there within say a particular period of 3 months or 4 months. Now after this much of tracks have been reported, then we convert those tracks into the concentration. And now with the advanced techniques, it is very easy to measure the damages with the tracks with the help of a spark counters. So BRC has given a formula which you could note down, or which of course we will be sharing these course material to you also. You need not to note it down right now. So depending upon the radon, upper formula means depending upon the track and the background. Days means the number of days for which this detector has been hanged. Generally, it is recommended to hang it for at least 3 months. Then again, the tracks per centimeter square per day. So roughly, if you say by using the effective equivalent concentration or the values of the tracks which we have measured after suspension of these detector for say 3 months, for 4 months, depending upon the seasonal requirements. Like in India, we generally have 4 types of seasons. We prefer to suspend these detectors within seasons of spring, winter, summer, and autumn, 3 months each for 90 days. We suspend these detectors, and this upper compartment and the lower compartment of the pinhole cup dosimeter, the lower one is called the radon plus thoron compartment. and the upper one is called the radon compartment. The reason is through these pinholes, the gas will enter from the bottom, and this is actually where it has been suspended. At least some protocols have to be followed while suspension of these dosimeters. The reason is it should not be affected by the direct building materials, because if you suspend it very close to the walls, the plaster of the walls which is having a cement concentration, that may give you an idea, that may give you an effect that how this cement or the natural material, natural building material which you have used, or even the tiles or different materials on the walls, they could also affect. So we just want to hang it in such a fashion that it is not affected by the outside environment in terms of building materials, because we want to measure only the natural that is within the air. So that is why they are suspended at least 1 to 2 feet below the ceiling and 1 to 2 feet away from the walls, so that the impact of direct building materials is not there. So only the air surrounding the detectors within the range of 3 or 4 centimeters could affect it, and finally it will give you an idea. So as the thoron is highly volatile, there are 4 holes which have been provided in this pinhole cup dosimeter. So out of these 4 holes at 90° to each other, if you could see from this cursor, at 90° to each other, there are 4 holes which have been provided, and these 4 holes allow the radon to enter into the second compartment, that is upper compartment, from the lower compartment. So in the first compartment, there is a radon plus thoron, and this thoron is restricted only to the first compartment, and only radon is allowed to pass through the 4 holes. Then these 4 holes allow the radon to enter into this compartment and finally affect the LR115 placed on the upper body. So this total pinhole cup dosimeter gives you an idea that the lower compartment is the radon plus thoron compartment and the upper compartment is the radon compartment. So if you measure the damage across the lower compartment or the lower detector, it is the damage which has been caused by the radon as well as the thoron, and in the upper compartment the damage is caused only by the radon. So you could see from this figure that this lower detector which is there, it is affected by radon as well as thoron, and the upper detector is affected only by the radon. And if you remove these detector after say 3 months and then do some chemical etching, which we generally follow in the sodium hydroxide, we will discuss those things in detail when we will discuss that how to exactly measure the value concentrations. So with the help of sodium hydroxide, these damages are being made permanent, and then finally the detectors are ready for the counting. And we use these formulas by measuring the number of tracks per centimeter square per day. We could estimate the effective equivalent concentration in terms of becquerel per meter cube. So in the first compartment, that is in the lower compartment, there is a radon plus thoron concentration, and in the upper compartment there is only the radon concentration. So if you reduce the radon concentration from the radon plus thoron concentrations, you are left with the thoron concentration. So that is why these 2 detectors have been provided. One gave you idea of radon plus thoron, another give you idea of radon, and the difference of those 2 is the concentration or the contribution of thoron, because there is no other way directly to measure the thoron concentration with a very simple technique. Of course there are some instruments, but this is a very simple technique. Detectors cost you around 1000 rupees. You can hang this detector, and this film also cost you very less, and then after 3 months you could have an exposure in the indoor environment. That what is the general rough idea of exposure of radon and thoron in our environment. And generally it is recommended that your internal houses action level for radon and radon is around 100 to 300 becquerel per meter cube. 100 is for new buildings and 300 is for old buildings. Sometimes it is being asked by the researchers or the students, sir, why there is a difference of 100 for the new buildings and 300 for the old buildings? Because even 300 becquerel per meter cube is not, it is a recommended action level, mind it is not the safe limit. So means if you are having exposure even 300 becquerel per meter cube, it doesn't mean that you have been exposed to very high level of radiations. It only means your exposure of natural radiation is little bit higher as compared to the other persons who are having lesser than 300. So it is recommended action level while designing or while manufacturing the houses or the dwellings. It is suggested that your choice of building material should be such that your exposure doesn't crosses the 100 for the new buildings. But in the old buildings, as we cannot immediately change all the type of building materials, we can only have a choice of little bit ventilation conditions. The exposure is at a little bit higher side. So it is best to have a maximum ventilation in the environment and that type of choice of building materials which give you a lesser exposure as compared to the other building materials like granite. If you use granite, it is naturally radioactive in nature, so it will give you more exposure. But if you use, instead of granite, if you use a sandstone, it will give you a lesser exposure. So choice of building material is also very important. So it is not only the field of a physicist or a environmental scientist, but architects, civil engineers, they should also sit together while designing the buildings, while designing the apartments, what type of building materials they should use. That also plays a very important role. So these are the another detectors which have been developed by the BRC people, Baba Atomic Research Center people, which we call as a DTPS and DRPS. And if you see from the previous finger, this is the DTPS and DRPS which are hanged together with the spin hole cup dosimeters. So if you see from this figure, this LR115 is having a filtered layer, filter paper is placed of a luminized mylar. On the one side it is around 50 micrometer, on the other side it is around 37 micrometer. The reason for this is, as I have already told you, that our film is sensitive for energy range of around 4.5 to 5 MeV. And from the DRPS, direct radon progeny sensor, there is a isotope of radon which we call as plutonium 214, which emits an alpha particle of the energy of the order of 7.69 MeV. Now this 7.69 MeV energy is higher as compared to the sensitivity of this detector. So to make this energy come into the sensitivity range, we have to use a filter. So this filter is approximately of 37 micrometers. And if you are measuring the thoron, that is 220, then one alpha is emitted, it comes out to be 216, and if another alpha is emitted, it comes out to be 212 polonium. So this 212 polonium emits an alpha particle of the energy ranging from 8.78 MeV. So it is little bit on a higher side as compared to the polonium 214. So we have to use a bigger absorber, so as a filter, so that excess amount of energy is being absorbed by this aluminized mylar, and finally only 4.5 to 5 MeV of energy is released across this alumina is mylar and falls on this LR115, so that it comes into the sensitivity range of our detector. So rest of the things are the geometry or the locks which have been provided. So this is a detector and this is an absorber. So on the one side, for detection of radon progeny, that is daughter product, that is polonium 214, we are using an absorber of around 37 micrometer. On the other side, for the direct thoron progeny sensor, where we are directly measuring the daughter products of thoron, that is polonium 212. So we are using an absorber of around 50 micrometer, because polonium 212 gives alpha particle of the energy ranging to 8.78 MeV. So of course, these are the minimum detection limits. For DTPS, it is 1 becquerel per meter cube. DRPS, it is 1 becquerel per meter cube, and for DTPS, it is 0.1 becquerel per meter cube. So this is the sensitivity range. Of course, we can also filter out the aerosols combinations by placing a wire mesh over this detector, so from which we could separate some minute and finer particles also. So that type of detection could also be done. So these are the few protocols for the measurement. Especially the important protocol is the choice of the seasons for which you are going to measure. Like I said, in India, generally we prefer 90 days in India, minimum 90 days, so that we could cover all the 4 seasons. But you could have a choice of 4 months also. That means you could divide the year into 4 months range. It's not starting from January only. You could have it from November, December, January, February, and then from March, April, May, June, and then July, August, September, October. So you could divide it as per the convenience of your cycles or even your seasons. Because even in India, if you say, the regional diversity is there and seasons are different in different areas. So the choice of the measurement should be taken in such a fashion that you prominently cover all the different seasons available. And then after 4 months or after 3 months, if you are using a 4 months, means 3 seasons channel, or if you are using a 3 months as a 4 season channel, you have to remove those detectors and finally do the chemical etching process, which I have already told you, that is around sodium hydroxide of 2.5 normal is used, and at around 60 degrees Celsius for 90 minutes we go for etching, so that the tracks become fixed. Then our tracks are visible, and you could count those with the help of spark counters, or previously we were using some of the optical microscopes or electronic microscopes you could use. And then again, the background track density, you have to take the measurements and finally remove those background parameters. And then based upon the concentration, you could calculate the final annual effective dose. And if you see the CRN, that is the concentration of radon, will give you the final annual effective dose. That depends upon the total year span and dose conversion factors. And finally, you could estimate the details. Now, similarly, with the help of a detector which is very important, that is RAD7, you could measure the radon concentration in water. And its operating principle is very simple. You just bubble out the radon gas present in the water with the help of the bubbling pump, and then from the bubbles, once the gas comes out, we go for the measurement. And this is a simple diagram. Of course, we will discuss those things in detail once we will be discussing the detail parameters. Then we are also interested in measurement of uranium in water. And for estimation of uranium in water, previously we were using the fission track registration techniques. Then we come to the laser fluorimetry. Now we are using LED fluorimeter and ICP-MS, which are the advanced techniques. So out of this uranium concentration in water, the important parameter generally we measure is the uranium 238, uh, because it is present in abundance. And if you see the concentration, more than 99% contribution is uranium 238 is present. And why it is important? Because uranium, suppose you are having a concentration of uranium in water, once you have collected some water samples, it is not possible, or you can't say that the source is the same from where you have collected. The reason is the hexavalent component of uranium, that is U6 plus, that is water soluble. So if the thing is water soluble, so once uranium is present, suppose a river is flowing and it comes into in alignment with the uranium concentration in some groundwaters, and the source is 100 kilometers away, but it is having hexavalent component, so that will be soluble in water and that will continue to flow across the river. So by taking the water samples from a particular place, especially in terms of rivers or channels or canals, you can't say that the source is the same. If you extract the groundwater from the soil with the help of hand pumps or some motors or other, of course, the source will be from that particular depth. But in terms of rivers or in terms of channels, the source may be 100 kilometers away. So that is why it is very important to have an idea that what type of measurements you are performing and how you are collecting the samples. Similarly, this is the process working principle of LED fluorimeter, which has been given to you. Like of course, we will plan some workshop also during this final day. We will show you some of the live demonstrations of processes where you could have an idea that how we are going to measure it. So we will be performing some experiments, and I would request Abhishek and his team to get ready for the experimentation process in the last day, where we were having some hands-on training to them, so that they could have a direct idea that how we are going to measure. Similarly, after measurement of radon concentration, uranium concentration, heavy metal concentration, we could measure the radium, thorium, and potassium in soil samples. And this is how we generally collect the soil, finally filter out those soils, crush those soils in a fine powder and dry them. And then, of course, to remove the water level, or we just dry those soil samples for 3 hours at around 100 degrees Celsius. Then the samples are being sieved, they are being measured, and finally they are packed at least for 3 months. The reason is the humidity has to be removed from the soil samples, and the packing is to be done in such a fashion that each container should match up with the geometry of the required geometry of your measuring instrument. So if you change the geometry of the measuring instrument or the geometry of this container, the results would vary. So that is why it is very important to use a right shape and size of the packing material in which you are packing the samples for at least 6 to 8 months before measurement, so that the naturally radioactive equilibrium could be attained before measurements. And then you could place those samples within the compartment available for this measurement process. And like this is the instrument which is available in our lab, that is a scintillation counter. So where you could place your sample and finally go for the gamma ray spectroscopy techniques for the estimation of different radium, thorium, and potassium concentration in soil samples. So similarly, for the assessment of heavy metal in soil and water, we could prepare those samples. Like in case of soils, I have told you that our instruments, either ICP-MS or AAS, they work on the liquid samples. So for in case of soil samples, we have to use a microwave digester, and with the help of those digester, we could convert our soil samples into the liquid samples, and finally we could use those techniques which we will discuss uh, in detail in our next lectures, and we could measure. So these are the few important reports which have been published by our lab and our department, where the Tribune, the Hindustan Times, and even Doordarshan, PTC channels, so many channels have published our reports, because we generally go on pinching the government also, like if there is a high concentration in some areas, so we have to bell the cat. So we go on giving our reports in the different newspapers, print media also, so that we also remain in public, and public should know that what type of work we are doing and how it is impacting their health. And recently, from our report, the Punjab State Human Rights Commission has taken a cognizance of our report, and they have asked the Punjab Pollution Control Board to check the high concentration of chromium levels in Jalandhar. So that is why these type of studies are very important. So these are the facilities or the pictures of our lab. So I invite all of you to visit our lab anytime you want. We are ready for making collaborations with the different institute also, like presently I am working as a dean research and consultancy. Also in India, we are having so many collaborations with different IITs, different NITs, and even the state government organizations, where we do the joint publications, joint research, and submit even some joint projects, and even some proposals for the workshops and the seminars. So we are welcome, we are open to everyone. You could always contact us. So these are my numbers and emails. So for any case you require, you could always contact me. And before starting the next lecture, we could take a break for 10 minutes, and then we will be starting at 2:35 for the next lecture. So any question or any query if you are having, I'm ready to answer it. So Abhishek, you could note down some of the queries which are there in that component, and like some people are writing some chat box also.
Okay, sir.
Okay. So
Thank you very much, sir, for such an informative talk. Dear participants, we will start the next session, lecture of the session within 5 minutes.
so I will be joining maximum by 2:35. Okay.
Okay, sir. Thank you very much, sir.
Thank you. Thank you. We could have 10 minutes break, and then I will be joining. Thank you. So, good afternoon once again, and we'll be starting our next session. So, I think it's visible.
Yes, sir, it's visible.
Yeah. So, welcome the participants for this last session of today's GIAN program, where we will be giving you a detailed idea about the uranium biokinetics in human adults and protracted ingestions of groundwater. So, like in the previous lecture, I have discussed various techniques for the estimation of natural radionuclides in air, water, and soil. This particular lecture will be dealing with the uranium biokinetics, which we are using. We are one of the pioneer lab in this region, or especially we could say in India, who are using the biokinetic modeling for the estimation of different doses to our different organs due to the concentration of uranium in groundwaters. Now, if you see the outline of the talk, we will be discussing a little bit about the routes of exposure, uranium in groundwater, and then biokinetic modeling, and some other different models of ICRP hair compartment model, and finally one case study I will be presenting for the estimation of uranium concentration in water, and finally calculations of the doses. Now, again, a similar type of a picture. Once we say it is a radiations are continuous from the lower energies to a very higher energies, starting from radio waves, UV, visible, infrared, microwaves, extra. So, and generally they are divided into two broader categories. One are the ionizing, another are the non-ionizing radiations. And out of these ionizing as well as the non-ionizing radiations, generally the ionizing radiations have more impact. Like the mobile phones which we are using, they are giving us the non-ionizing radiations. So though we are having mobile phones continuously with us 24 hours, rather I could say nowadays, so they are giving you some impact, but their impact is not so high as compared to the exposure from the ionizing radiations. Because the ionizing radiations give you more impact as compared to the non-ionizing radiations, because radiation exposure, which I was discussing in my previous lecture also, that is as far as the United Nations report is concerned, UNSCARE's report is concerned, that is 2.4 millisievert. And out of this, and out of this 2.4 millisievert, this nearly 1.15 millisievert or even up to 1.5 millisievert is only due to the concentration of radon. So there are different routes of exposure to our body, that we could have some external exposures, we could have some internal exposures. So external exposures, if you see from the figure, it is giving you an idea about how the exposure is entering, like you have inhaled something, it is entering to your body through your inhalation process, then it is depositing within your lungs and even your kidneys, even your intestines, and finally affecting you. There are some internal exposures also. So internal exposure means inhaling radioactive material in air, ingesting contaminated foods and drinks, then inadvertent ingestions, absorptions through the skin or open wound. So that is also some of the types of internal exposures are there. Now, if you see the quantified intake by ingestions or inhalations, so based upon your quantified intake, that how much you have taken as input, either you have ingested something or you have inhaled something, we use the different models which we call as a biokinetic as well as the dosimetric models to have an estimation of the quantified intake of ingestions or inhalations. And then we use these models to estimate the mean absorbed doses in the organs and tissues. So like if I drink 2 liters of water per day, so my exposure will be different from a person who takes 4 liter of water per day for a same type of a body weight, for a same type of a exposure. The reason is because the natural uranium contamination in 2 liters of water and 4 liters of water is different. So depending upon the type of intake, that is the quantity of intake, some of the factors are being applied. Then if you apply radiation weighing factors, then from the absorbed doses, you could calculate the equivalent doses to an organs or tissues. So that means my lungs, my heart, my chest will be behaving differently for a same type of intake. And then applying the tissue weighing factors of my different tissues, I could finally calculate the effective doses to the different organs. So which we generally call as a gonadal doses. So like if I drink 2 liters of water, my exposure to lungs will be different. For a same intake of 2 liters of water, my exposure to kidneys will be different. For same intake of 2 liters of water, my exposure to bones is different. So depending upon the different weighing factor, radiation weighing factors and the tissue weighing factors, my exposures are being calculated in details. And you can't say that if the rate of concentration of or 60 ppb or 60 microgram per liter, it will be giving a same impact on my lungs, it will be giving a same impact on my heart. No. So for different organs, the same concentration will give a different type of impact. For different tissues, the impact will be different. For different age groups, the impact will be different. For different sex, the impact will be different. So for different concentration of different salts or the exposure in the water, the effects will be different. So there are two parameters. One is if the concentration of uranium is different in different soils or in different waters, impact will be different. It is very true. But for a same concentration of water, same concentration of uranium in water, the impact on different organs will be different. So it is very important to study the impacts of different organs instead of saying that this much concentration will give you this much of impact, because it is a general estimate that if the exposure is this much, my impact will be different. My impact will be this much. My effective doses will be different. But for my heart, the doses will be different. My lungs, the doses will be different. For my bones, the doses will be different. So it is very important to calculate the different tissues weighing factors also while measurements are being carried. Now, if you see the uranium, it is present since the Mother Earth, and half-life is, the life of Earth. And from the very beginning of Earth, uranium was present, and still the age of Earth is the half-life of uranium. That is for 4,500 million years. So uranium is groundwater. Why it is important? So it is a lithophilic element which is having five different rather valence states: 2 plus, 3 plus, 4 plus, 6 plus. And out of these 2, 3, 4, 5, 6, the 4 is insoluble in water and the hexavalent is soluble in water. So if you are having more hexavalent contribution valence states present in that particular water samples, so that is once, even in the mountains, even in the glaciers from where the rivers or the channels are flowing, so if the mountains are having more 6 plus valence state, so it will be soluble in the water running through across that mountain, across that channel, across that glacier. So source may be in the Himalayas, but impact may be in the Gangas. So source may be in the Himalayas, impact may be in the Calcuttas, where the deltas are there. So you can't say that if the concentration is high at a particular place, the source is also at that place. So source may be from different places. So that is why it is very important to have an idea of the geology of that particular area before reaching to some of the final conclusions. Because what happens that sometimes we say that this is the concentration and this is the impact, so this area is not good for living. So it is not there. You have to understand the basic idea that how the geology of that particular area is responsible, whether that geology is contributing or whether some different source is there which is contributing to the high concentration. And to your surprise, in my area, especially in Punjab, where there are a lot of cases of a high level of uranium concentration in Malwa region of Punjab, lot of studies have been carried out. Different researchers have published different reports and published different papers where they have said that in some areas of Firozpur, Faridkot, Mansa, Bathinda, the level of concentration of uranium is very high. But to your surprise, even within a same village, the concentration is high in some of the areas, and within the vicinity of 100 meters, the concentration is within the safe limits. So how it is happening? So it was very surprising for we people also that if the concentration of groundwater is high in a particular hand pump or a tube well where we have extracted the groundwater from a particular place, within the vicinity of 100 meters, the concentration is very low. So then we have to take the help of the geologists, where we could make out some of the conclusions, but still it is not the perfect conclusion, I would say. But still a lot of detailed investigations are required, that some of the areas in that particular regions, they were having some perched layers. It was a waterlogged area. So where water has been interlocked within some of the perched layers, and that perched layers, the water concentration was due to the high level of granites which were present in the geology of that area, and it has high concentration of 6 plus valence state, which is water soluble, and with the mixing of granite with the groundwater, the concentrations were high in some of the areas. So that is why it is very important to understand what is the geology of that area, and then enters groundwater aquifer due to the natural geochemical processes like mineral dissolutions and the desorptions of absorbed uranium from the mineral surfaces. That is also important. Anthropogenic contributions, we have to understood that what are the anthropogenic concentrations in those areas, what are the industries, what type of industries are present in those areas, what type of activities are going on in those areas, whether they having some fertilizer plants, whether they are having some thermal power stations, whether they are having some nuclear facilities. So those things are also very important to understand, to have an idea of the anthropogenic contributions. Then hexavalent species UO2 plus, so that is also important to understood. And then finally you have to understood that what type of contacts you are using, like whether you are drinking the groundwater or whether you are ingesting some food samples or whether you are coming into the dermal contacts. So that is important. Now, this principal sites of uranium depositions in the body, they are important organs like kidney, liver, and bones. So those are the three important parameters. And now the hairs, that is your hair present in your body, they are also the major contributor. So how it is dangerous, uranium is dangerous. So from the figure you could have an idea that you could have a high blood pressure, you could have some kidney diseases, you could have some reproductive functions, you could bear some bone cancers, you could have some kidney functions, you could have some lung cancers with the high concentration of uranium. Some are the chemical effects on the left side, radiation effects on the right hand side, which we have mentioned. And the sources of uranium in the groundwater, one is the natural sources of uranium in the groundwater, means like I said that you are having some geology of such mineralizations or rocks that your groundwater is naturally radioactive, like if you are having more granite in those areas, so that may be one of the reasons. Then there are some anthropogenic activities also. Anthropogenic activities means if you are using more pesticides, more agriculture fertilizers, again some waste of nuclear power plants or wars are there, then mining activities are going on, means if you are having some nearby mines areas, so those are anthropogenic activities, they may also contribute. And there are some cosmogenic activities also which are there but they contribute very less. So most of the contribution is due to the geogenic, that is weathering by steam streams of uranium rich rocks, which I have already told you that if your mountains are having more hexavalent components, so they are water soluble, so any water body which is traveling through that source, they will have more concentrations. Then there are some anthropogenic activities. Now, these are the source pathway receptor analysis of uranium. Like if you start from the very beginning, from the atmosphere, you could have concentration into the soils, concentration into the fresh waters, concentration into the urine and marine waters, and then from the soil and fresh waters, they are again interlinked with each other. You could have a concentrations to the groundwaters, you could have concentrations to the sediments, and then again from the third component, that is the marine waters, you could have concentrations to the sediments. So these are the spatial distributions which have been represented in the dotted block lines at the upper, which are the sources. So from this, it could be bioaccumulations or exclusions, and then you could inhale it from the sediments, and you could ingest it from the soil sediments and drinking water. And then from the bioaccumulations means if the plants absorb those high concentrations, or if the animal take the intake from those high concentration, say cattle feed, so they could again be given back to the human beings in terms of once we take those plants as our vegetables, and once we take milk products from those animals. So it could be ingestions of plants and the animal products, which could again give us the exposure. So we are having different environment, but from all the environment, the assessment or impact on humans is there. So we could see from this figure that from the spatial redistribution to the bioaccumulations, final concentration is coming to the receptor as the humans. So then there were different models which have been suggested by different scientists. The first biokinetic model was proposed by Bernard and Strunes in 1957. So basically they were dealing with the blood, bone, kidney and urine. Means how this uranium from the blood is excreted in terms of the excretion, either is a urination or a feces, and then how this concentration is distributed across different bones and other organs. So this was the initial model which was started. Like if you take an intake of water or an intake of high concentration of uranium, so how it will be excreted out. So the best way of excretion was the feces as well as the urination, which was understood at that time. So kidney was also considered the most susceptible organs to the radiation damage rather than the bones. So generally we say that if our concentration of uranium is high in terms of water concentration, so our kidneys will be mostly affected as compared to the other organs like bones. But then with the advent of new sciences and the technologies, the ICRP published new models which we call as ICRP2 biokinetic model of 1959 and ICRP systematic biokinetic model of 1995. So if you see from the figures on the upper model, from the blood plasma, the concentration was given to the bones as well as the kidney, and finally it could be excreted out in terms of urination or feces. But in the systematic biokinetic model, which was a revised model in 1995, which was published by the ICRP in the 69th publications, these all models are available free of cost on the ICRP website, International Commission of Radiological Protection's website. You could have or download those models or parameters from their publications, and finally you could understand what are the different advancements in different models due to the work done, of course, for a prolonged period of time, how they have interpreted that, how the intake of uranium concentration is affecting our different organs and how we are excreting it. Now, from the ICRP 1995 model, if you see, the concentrations have been distributed to different bones, and kidneys component have been also distributed, because sometimes we have a very high exposure immediately after we drink something, and later on our plasma go on excreting it, and finally with the help of urination and feces we are excreting out from our body. Then final important model with the advent of new sciences and understanding of technology was developed by W.B. Lee, which we call as a 2010 hair compartment model of uranium. So if you see from this figure, from the blood plasma, it is going to our livers, it is going to our small intestines, it is going to our upper large intestine, it is going to our kidneys. It's a two-way. You see the directions of the arrows. It is flowing two-way, means from the kidney again it is coming to the plasma, from the plasma it is going to the kidneys, from the liver it is going to the plasma again, from the liver it is plasma, it is going to the livers. So if you see the ingestion component, once we ingest something, means if we eat something, so it enters to our stomach, then from our small intestine it goes to the blood plasma, and again from the blood plasma it goes to our large intestine. So from small intestine it is directly going to our large intestine, and even from the blood plasma it is going to our large intestine, and then to the lower large intestine, and finally we excrete in terms of feces. That is, we have ingested something and we have excreted something. Now in terms of body or bones, which we call as a skeleton or a trabecular surfaces, cortical surfaces, so cortical volume and trabecular volume is very important, so bone density is very important. So again it is going to our blood plasma and finally going to the kidneys, and from the kidneys to the urinary paths, and from urinary paths to the urinary bladders, and finally we excrete in terms of urination. So these were the few models which were available at that time, that we could excrete either in terms of feces or we could excrete either in terms of urination. But the third component which was added at that time was the hair, that is our hair present in this body. So from the hair it was informed that, or from the model it was predicted that nearly 31.5% contribution of excretion is through the hairs. So which was very surprising. And it was also proved in some of the documentaries or in some of the researchers that if you are working in some high radioactive areas, so your hairs have a high concentration of uranium contaminations or those radioactive contaminations. So even these type of activities were used by some of the investigating agencies for collecting the hair samples from the barber shop of some of the scientists and estimating whether they are working in some restricted areas, in some nuclear areas or some radioactive exposure areas. So from the other soft tissues or from the hair, the excretion is nearly 30%. So that is why it supersedes all the ICRP's previous biokinetic models. And we now have three channels of excretion. One is the urination, another is the feces, and the third one is the hair. So this is one of the case study which I will be presenting to you, which we have done a survey of the biokinetic studies of uranium ingestions through groundwater in Chittorgarh district of Rajasthan area. So Rajasthan is in the western side of India, and most of the district we have tried to cover it. We have made a grid map of around 10 kilometer by 10 kilometer scale, and then we tried to cover the maximum grids depending upon the availability of the transportations in those areas. So we tried to cover some of the grids, and these are the few limits which you should understand. What are the few maximum contamination levels given by different agencies for the human beings? The WHO and the US EPA, that is the United States Environmental Protection Agency, has given a safe limit of 30 microgram per liter. So if your concentration is within 30 microgram per liter, it is safe for drinking purposes. So it will not be affecting you. So Anscare in 2000, they have given a limit of 9 microgram per liter. So microgram per liter is basically the concentration in ppb, that is parts per billion. And in India, the EERB has given a limit of around 60 microgram per liter. And now why there are ICRP has given a 1.9 microgram per liter as a safe limit. So of course it is working with the radiation workers, so they have been exposed for other radiations also. That is why the limit is very less. So from the water, if you get this much of exposure, because you are working in some radiation areas, so you are being exposed. So that is why the safe limits for the radiation worker is very less in case of ICRP, that is 1.9 microgram per liter. But for Indian people, generally it is of the order of 60 microgram per liter, and it has been calculated on the basis of criteria that how much water we generally take. Generally for a case of adults, we take average intake of 2 liters. So based upon that 2 liters of intake, it has been calculated as 60 microgram per liter is a safe limit. Also, it depends upon some of the physical conditions or biological conditions of different ethnic communities. Like we as Asians or Indians have a little bit more safer limits as compared to the European countries. So that is why our limits are little bit on a higher side also. And this is the methodology which I will be discussing. That how we are going to measure it, and we will be giving you the live demo of this measurement also during the 5th day, where we will be using the different fluorines and calibration modes. Finally, we will be telling you that how you have been measuring these uranium concentration at a different parameters. So this is our sample holder, this exposure which cursor I'm showing. So this is our sample holder. So where we place our sample in a quartz container, and finally with this working principle of fluorescence of uranium complexes in aqueous medium, we measure the uranium concentration, and measurement time is very small. It takes around 1 second for an average of 256 pulses taken 5 times. And this instrument has a analytical range of measurement, that is 0.5 microgram per liter or ppb to 1000 microgram per liter or ppb. And with the help of this, we measured at different locations in our samples, and we found that apart from this one red colored sample, in most of the cases, the concentration is within the safe limits prescribed by the Atomic Energy Regulatory Board of India. But if you talk in terms of WHO also, there are 2 samples which are having higher values of uranium concentration. And if you take in totality, there are 3 samples only in 3 villages where the uranium concentration was higher. So what we tried to correlate it with the geology of that area also, which I will be discussing in our next lectures, that how the different concentration of soil samples is impacting the concentration of uranium contamination in water. So then we calculated the detailed analysis with the help of some geologists, and we studied in some of the areas. So we found that there are some uh, geological parameters which are responsible for giving a high concentration in those areas. So which we'll be discussing in our next lectures. Now, based upon this, we applied the hair compartment models to our concentration, and if you see from the hair compartment model, so we calculated the different organs component. So we calculated it for kidneys, we calculated it for liver, we calculated it for lungs, we calculated it for pancreas. So this is the concentration distributions which has been given or shown, that how it is being there. So if you see the values from this, the bone surfaces has around 38% of concentration, and then from the bone surfaces you could imagine that maximum retention is on the bones. So from this, we concluded that out of the 32 water samples, the uranium concentration in 3 samples were exceeded the recommended action level or recommended well limits of WHO and US EPA, and only 1 sample exceeded the limits of Atomic Energy Regulatory Board. So, like I have told you that we have done some geological calculations also. So there are some biotite materials present at a depth of around 300 feet. So due to those biotite materials, the concentration was high in those nearby villages. So which is again a part of concern for us. So which act as a subsorption elements for the uranium. So those biotite materials were present in those areas. So we are we have extended our research in that particular area also, where we are working on some of the natural development of natural polymers, so which could remove those uranium concentrations from the groundwater samples, and they could absorb. And we have attained a very successful result with the help of some banana leaves, that we have developed some polymers with the help of banana leaves. We have extracted the cellulose from the banana leaves and then used that cellulose for the um, removal of uranium contamination in the water samples, and we have achieved nearly more than 90% of removal. So again, we will be discussing those things in our next lectures, when we will be discussing some of those materials. So we found that infants between the ages of 7 to 12 months are the most vulnerable to the radiation exposures among all the populations and the age groups. So the reason for this is, like most of the infants at the ages of 7 to 12 months were depending upon the lactic mothers, and for lactic mothers the concentration or the water intake by their mothers is also impacting them. So they are being breastfeeded by their mothers, and finally they are being affected. So, however, even for the most vulnerable segment of population, that is children, the toxicity hazards analysis provides reassurance that the predicted levels of uranium exposures is modest, indicating negligible chemical risk. So, external hazard quotient for all the areas was less than 1. So, that is, the drinking water is safe for the local populations. It's not so much dangerous. So some of the remedial studies of a urinal from the aqueous solutions using the cellulose extracted from the leaf of banana, which I was discussing. So I will be giving you an idea about that how we have extracted it. So we have collected some of the banana leaves. Then those were fresh collected, washed banana leaves were there, then oven dried so that the moisture content could come to the level less than 5%. Then we have crushed it. Final bioabsorbed cellulose from the banana leaves have been extracted, and final product is generated. So this is a little bit time consuming techniques, but I am just giving you an idea so that you could have an idea that how this banana leaves are useful for the extraction of uranium concentration. And then we have done different transmittance analysis, and we have done their XRD analysis. We have done some SEM studies to prove that the cellulose is being generated. And from the different batches, we have prepared the standard solutions of different uranium concentrations. For 10 ppb, we are having standard solutions. For 100 ppb standard solutions, we do the batch analysis for because once we do the batch analysis, we have to take a standard also. So we compare the water samples with our standard solutions, which we prepare as our buffers, with the known value of concentration of uranium. So for 10 ppb we have done, for 100 ppb we have done with those standard solutions, and we have measured the uranium concentration. And what we have found that the absorption, once this cellulose was put into the water samples, the absorption efficiency or efficacy was around 90%, starting from 60 to 90%, and it was not affecting with the absorbent dose also. And finally, contact time we have taken from 15 minutes to 60 minutes. It was giving us a fair results that no deabsorptions was occurring even after 60 minutes. So once it has absorbed within the 15 minutes, we keep it there for further 60 minutes and to see whether some deabsorption is occurring. But our results were very satisfactory, and no deabsorptions occurred even after 1 hour. So then from this study, we concluded that the greatest uranium absorption effectiveness in the aqueous solution was, the maximum which we achieved was 96.69%, and generally it's of the order of 90%. So absorption studies from the uranous ions from the aqueous solutions was influenced by various factors, pH, that is the percentage of hydrogen, ion concentration, and the applied doses. Of course, they are the responsible parameters, and we have kept the ideal pH value for this is 4.5. So the ideal parameter for achieving the highest absorption efficiency were at pH 4.5, because we have tried at different pH values. So at 55 ppb, strong ion concentration and 10 milligram applied doses of uranium solutions in 10 ml of water. So at pH 7, the lowest absorption efficiency was measured at around 16.65%, with 55 ppb of the starting ion solution and 10 milligram of applied doses. So the best value which we achieved was for the pH 4.5. The experimental data plot shows that no influence of contact times, which I have discussed, that no deabsorption occur even after 60 minutes of exposure. Then the cellulose which was derived from the banana leaves was found to be effectively removing the uranium ions from the aqueous solutions. So banana leaves can act as a natural polymers. So we are working along with our colleagues in our institute by development of some other natural polymers with the help of some different plants and different naturally available plants where we are extracting the cellulose from those plants and finally developing some of the bioabsorbents, so which are capable of removal of not only the uranium concentration but other heavy metals also. So we are working on cadmium, we are working on chromium also. So we are working on different heavy metals where development of the natural polymers is giving us a good results, and we have published our results in very good papers. And of course, you are again welcome to visit our lab, and especially the chemical engineers and the chemistry people who are working in the development of the bioabsorbents. So we could collaborate with them so that we could have an idea that how we could develop some pallets type of polymers, so that we could fit those pallet type of polymers into the filters, and finally with the help of those filters we could remove the heavy metal as well as the uranium concentration from the water samples. And secondly, another thing which is important is like of course these are the facilities which are available in my lab. So we are having ICP-MS, we are having gamma ray spectrometer, AAS, LED fluorimeter, and RAD7. We invite the different chemical engineers as well as the chemistry people to give us more information about the development of the polymers, because though we are working in these particular areas of a natural environmental radioactivity, but important parameter is like how to remove it. So we could estimate it as a physicist, we could say that this is the concentration, but how to remove it, there the role of some chemical engineers and chemistry people is very important, because they are having good expertise in development of the polymers. So we have achieved some of the removal components or removal pallets we have developed with the help of cellulose nitrate or cellulose materials extracted from the banana leaves. We are working in some other natural polymers also, but still the lot of intimacy from the different interdepartmental activities is required to reach to the final conclusions. So that is also the basic purpose of research. You can't restrict yourselves to a particular area, because I cannot be expertise in all the fields. So if I'm expertise in measurement, so one should be an expertise in the removal. So it is not only one thing is important, that I could say that this concentration is very high in this area and this area is very dangerous. So I have to give some solutions also. So for those solutions, we have to collaborate. So of course, these are the atomic absorption spectrometers which is available with us, and we are measuring chromium, cadmium, lead, copper, manganese, zinc, and another even mercury and arsenic. So nearly 16 heavy type of heavy metals we are measuring, and we are giving the consultancy to the different food industry, chemical industry, even our local municipal corporations to have an idea about the concentration of heavy metals in the water. So of course this is again a Agilent's plasma coupled spectrometer which is available in my lab. So you could always come and visit to us. So with this, we conclude for this lecture, and if any queries are there, so you could always ask, and we are free to answer those queries. And I am thankful to all the listeners, and I hope that during the next 4 days also, because this is a 5 days course, so next 4 days we will have your active participation, and I would request you that at least if you have some queries, you write down those queries in the chat box or the message box, so that we could note down those queries, and finally during the final day we would like to answer those queries, because it's a two-way process. So Government of India has taken a very good initiative where they have invited some of the experts from the foreign universities. so who are available to you, and they will be presenting their research. And but if you don't ask questions, if you don't have queries, so then by just one way of communication or a delivery is not important enough. So I would request all of you to be an active listener or active participant. And I once again thank all of you for being a patient listener. So with this, I would request Abhishek to conclude this first day of GIAN course. Abhishek, are you there?
Yes, sir. Thank you very much, sir, for sharing such valuable insights and making our session so enriching. I also thank all the participants for their patience, active engagement, and enthusiasm throughout the lectures and other sessions. We look forward to seeing you tomorrow for the next sessions with the Professor Shinji Tokonami, which will begin promptly at 10 a.m. So with this, I conclude.
Tomorrow's session is at 10 a.m., not at
Yes, sir.
10:30. No? So
Yes, sir. So
in the
tomorrow.
morning we will be starting at 10 a.m. So I request all of you to join at least 5 minutes before or 10 minutes before the 10 a.m. So thank you once again, and hope for the best. Enjoy your winters. Thank you.
Thank you very much, sir. So with this, we conclude the session for the day one. So
Thank you. God bless you.
thank you, sir.